Good evening, everyone. Good evening. I welcome you all again to VJ Enthuse. I hope you guys are doing great, having a good time. Well, people, you can just let me know in the chat box if I'm audible and visible to everyone. Just let me know in the chat box if I'm audible and visible to everyone, people. Welcome back, welcome back, welcome back. Just let me know fast. Just let me know fast if I'm audible and visible to everyone. I'm doing good. Aisha, I'm doing good, thank you. Good evening, Harita. Hello, Shankar. Hello, Abhivia. Hello, Vijay Lakshmi. Hello, Ashwarya. Welcome back. Hello, Tech Vlogs. Welcome back, people. Welcome back. Hello, Shailendra. Hi, Fazan. So, people, as you all must be knowing, tonight we are going to do something called as electronic configuration. I'll be exactly showing you how to write the electronic configuration of different elements. What are the exceptions which you have to remember in this? What are the rules which you need to take into consideration while writing the electronic configuration of different elements? Yeah. So before starting the session, the ones who are new to the channel, let me introduce myself. Well, people, my name is Wasim Bhatt and I'm your chemistry master teacher writer on this VJ Enthuse channel. Yeah. The ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this VJ Enthuse channel. Yeah. So do like the video, share the video with your friends, and do subscribe to the channel as well. Okay. So before starting the session, you guys can let me know in the chats if you guys are super duper excited about the session as well, right? Just let me know in the chats if you people are super duper excited for the tonight's session. Right, people? Aisha, the next chapter is going to be redox. The next chapter is going to be redox. Redox, thermodynamics, then periodic classification, then chemical bonding. This is going to be the sequence which I'll be following. Yeah? So just let me know in the chats, people, if you are super duper excited about the session. Shreyans, there's a link in the description box of the same video which you are currently watching. Click on the link, then you can edit there and use the coupon code WBPRO while enrollment, by means of which you'll be getting some additional 10-20% off. Yeah? Okay. Perfect. So let's get going. Let's get started. Let's see exactly how do we write the electronic configuration of different elements, right? But before talking about how to write the electronic configuration of different elements, in the last session, we talked about something called as quantum numbers, right? Okay, let me just quickly recap some things which are needed in the today's session, right? Then we'll be moving on to something called as electronic configuration, right? So people, in the last session, we talked about 4 quantum numbers, right? Out of which one was principal quantum number, one was azimuthal quantum number, one was magnetic quantum number, and at the end, there was the spin quantum number, right? We talked about those quantum numbers in detail, right? Okay, first thing. If I talk about shell number 1, n is equal to 1. It represents which shell? It represents the K shell. As you all must be knowing, it represents the K shell, right? In the first shell, people, there is only one subshell, and that's what we call as S subshell, right? That's what we call as S subshell, okay? And in that S subshell, there is only one orbital, okay? Which is, this is the way by means of which I designate that. One S orbital is there in case of the first shell, correct? So if I talk about shell number 1, there is only one shell. In that one shell, there is only one subshell. In that one subshell, there is only one orbital, and that orbital is what we call as one S orbital, right? Similarly, if I talk about n is equal to 2, that means I'm talking about the second shell, correct? Which we designate as L shell. For n is equal to 2, that means the second shell. In the second shell, there are 2 subshells. One is going to be S subshell, one is going to be P subshell, correct? One is going to be S subshell, one is going to be P subshell. People, in case of S subshell, there is only one orbital, that is 1s. And in case of P subshell of the second shell, there are 3 orbitals. One is going to be 2px, one is going to be, this is 2, correct? This is not 1s, this is 2s. This is going to be 2s, this is going to be 2px, then comes 2py, then comes 2pz, right? So these are basically the 4 orbitals in your second shell, yeah? Similarly, if I talk about shell number 3, in shell number 3, what do we call this shell as? This was KL, now comes the M shell. In the third shell, how many subshells do we have? We have got 3 subshells. One is going to be S subshell, then comes your P subshell, then comes your D subshell, right? And in s subshell, there is only one orbital, which we represent by 3s. In p, there are three orbitals of p, right? One is going to be 3px, one is going to be 3py, another one is going to be 3pz, right? And similarly, in case of d subshell, there are five orbitals. One is going to be 3dxy, one is going to be 3dyz, one is going to be 3dzx, one is going to be 3dx square minus y square, another one is going to be 3dz square. These are the orbitals which are present in your third shell. Similarly, you can check the orbitals which are there in the fourth shell as well, okay? Now people, this is the orbital which is there in the first shell. These are the four orbitals which are there in the second shell. These are some orbitals which are in the third shell. And similarly, there will be some orbitals which will be there in the fourth shell, right? Now what we exactly are going to do? We are going to fill the electrons in these orbitals basically. We are going to fill the electrons in these orbitals basically. But before that, let me give you the general overview of certain things. What are those things? Have a look exactly what I'm going to talk about. See people, if I write something as 3d x square minus y square, and over here I'm writing 1. Over here I'm writing 1. What all things can I conclude from here? What all things can I conclude from here? That is the point. Understand. See guys, it simply means this electron is present in the third shell. This represents the shell number. This represents the shell number. In the third shell, in which subshell electron is present? The electron is present in the d subshell. The electron is present in the d subshell. And in the d subshell, in which orbital the electron is present? The electron is present in dx square minus y square orbital. And how many electrons are present in dx square minus y square orbital? There is only one electron present in dx square minus y square orbital, right? Similarly, if I write something like this, 4dz square, and over here I'm writing 2. Over here I'm writing 2. What does that mean? It simply means these two electrons are present in shell number 4. This is the shell number. In the fourth shell, the electrons are present in d subshell, right? The electrons are present in d subshell. And in the d subshell, the electrons are present in dz square orbital. And in dz square orbital, how many electrons are present? There are 2 electrons present, right? So I hope you got the meaning of this general terminology, correct? Now people, before writing the electronic configuration of certain things, right? Before writing the electronic configuration of certain things, as I told you, you need to have a clear picture of this general notation, okay? I'm sure it's clear to everyone, yeah? Right? Perfect, guys. Now, there are certain rules which you need to follow in order to write the electronic configuration of different elements. Out of those rules, the first rule which you need to know in order to write the electronic configuration of different elements, that's what we call as Abba's principle. That's what we call as Abba's principle, yeah? What is this Abba's principle all about? See, guys, before talking about Abba's principle, in your first shell, there is 1s. In second shell, there is 2s and 2p. In third shell, there is 3s, 3p, 3d. In fourth shell, there is 4s, 4p, 4d, 4f, etc. Right? Okay. These are basically the subshells which are present in the different shells, right? And as you all must be familiar with the fact, your s subshell contains only one orbital, right? Every s subshell contains one orbital. P subshells, they contain 3 orbitals. One we designate by px, one with py, another one with pz. Again, this is s subshell, it contains 1 orbital. This is p subshell, it contains 3 orbitals, right? And this is d, it contains some 5 orbitals, right? Again, s comes 1 orbital. Again, p comes 3 orbitals. Again, d comes some 5 orbitals. Again, f comes some 7 orbitals, and so on, right? I'm sure it's clear to everyone till here, right, people? Now, first of all, in these orbitals, we are going to arrange the electrons. In these orbitals, we are going to arrange the electrons basically. When we write the electronic configuration, we arrange the electrons in these orbitals. Now, there are certain rules which you need to follow while writing the electronic configuration. While filling the electrons in these orbitals, there are certain rules which you need to follow. Out of them, the first rule is Abba's principle, right? What this Abba's principle is all about. Understand, people, what I'm going to say. Okay, I'm writing its statement. The statement of Abba's principle, then I'll make you understand what this Abba's principle is all about, right? Okay, as per Abba's principle, electrons electrons in the orbitals are to be filled on the basis of the increasing energies of these orbitals. The electrons in these orbitals are to be filled on the basis of their increasing energies, That means that orbital which contains the lowest energy must be filled first, then comes the orbital containing higher energy, then comes the orbital carrying higher energy, then comes the orbital carrying higher energy. So electrons in these orbitals are to be filled on the basis of their increasing order of the energies, right? Now the point is, how we'll get to know which orbital has got lesser energy, which orbital has got more energy, right? As per our Bose principle, electrons in these orbitals are to be filled on the basis of their increasing energies, right? So that orbital which contains the least energy must be filled first, right? Now how will we get to know which orbital contains low energy, which orbital contains high energy, right? There is a rule for that, which is only valid for multi-electron system, right? And that rule is something which we call as Bohr-Bury's rule. That's what we call as Bohr-Bury's rule, or you simply call it as N plus L rule. This Bohr-Bury's rule, it is going to give me the idea about which orbital has got the less energy and which orbital has got the more energy. And this Bohr-Bury's rule, it is valid only for multi-electron system. Multi-electron system means containing more than one electron, right? Okay. Yes. Now we will understand. As per this Bohr-Bury's rule is concerned, that orbital whose n plus L value will be less, will contain less energy. And that orbital whose n plus L value comes out to be more will be absolutely having more energy. Yes. Now people, if two orbitals will have same n plus L rule, if two orbitals will have same n plus L value, right? In those two orbitals having same n plus L value, how do we differentiate which orbital has got less energy, which has got more energy, right? These two orbitals which have got same n plus L value, how do we differentiate among them which one contains less energy and which one contains more energy? Remember, those orbitals which have got same n plus L value, okay, for those orbitals, the one which will be having the lesser value of n will have lesser energy, and that orbital which will be having more value of n will be definitely having more energy. This is something which you need to remember, which you need to take a note of, correct? Yes? Yeah? Now we will understand. Let's try to use this rule. Let's try to arrange these orbitals on the basis of their increasing energies. And once we arrange these orbitals on the basis of their increasing energies, and then let's try to fill them on the basis of their increasing energies only. Yeah? Right, people? Now understand how this Bohr-Bury's rule is used. See guys, if I start with 1s, if I'll ask you what is the value of n for this 1s, you'll clearly say the value of n is 1. What is the value of azimuthal quantum number L for this s subshell? That is going to be 0, right? N plus L value comes out to be 1 for 1s. So for 1s, the value of n plus L comes out to be 1, right? Similarly, if I talk about 2s, for 2s, the value of n is 2, and the value of L for s is going to be 0, n plus L value 2 plus 0 comes out to be 2, right? Similarly, if I will be having something called as 2p, in case of 2p, the value of n is 2, and the value of L for p is 1, so 2 plus 1, n plus L, 2 plus 1 comes out to be 3, right? Similarly, if I'll be having something as 3s, for 3s, the value of n is 3, the value of L again is 0, so 3 plus 0 comes out to be 3, right? Similarly, if I'll be having 3p, in case of 3p, the value of n is 3, and the value of L is 1, 3 plus 1 comes out to be 4, so the n plus L value comes out to be 4, as simple as that, right? Okay, and similarly, if I'll be having, for example, 3d, In case of 3D, what is the value of n? N value is 3, and L value for D subshell is 2. So 3 plus 2 comes out to be 5, and plus value L value is 5 for 3D, right? Similarly, guys, if I talk about 4s, in case of 4s, the value of n is 4, the value of L is 0, so 4 plus 0 comes out to be 4, right? Similarly, or let's keep it as such, right? Okay, right? Let's keep it as such, or let's write 4p also first. N value is 4, and L value is 1. N is 4, L is 1, so 4 plus 1 comes out to be 5, right? Yes? Now we will understand. For 1s, the value of n plus L came out to be 1. Value of n plus L came out to be 2 for 2s. Value of n plus L 3, right? N plus L 3, n plus L 4, n plus L 5, n plus L 4, n plus L 5. Now I'm going to arrange these orbitals in such a way that n plus L value, that orbital which has got the lowest n plus L value will be having the lower energy, right? So which orbital has got the lowest n plus L value? As you can see among all, the lowest n plus L value is there for 1s. So 1s has got the minimum energy among all, right? Followed by n plus L value is 2, followed by 2s, right? Then followed by what? Followed by 2p. See guys, 2p and 3s both have got same n plus L value. And whenever I'll be having two subshells having same n plus L value, at that time you need to see the value of n, right? See, this one has got the lowest n value among these two, so definitely 2p is going to have lesser energy, then comes your 3s, right? So 3s is done, now is 3p, then is 3d, right? Now I'll be writing 3p, okay? Now after 3p people, 3d has got n plus L value as, just a second, right? 3d has got n plus L value as 5, 4s has got n plus L value as 4. So which one has got the lower n plus L value among these two? 4s. So after 3p, I'll be giving preference to 4s, and after 4s, I'll be giving preference to 3d, right? So this is basically the increasing order of energies of these subshells, which I need to remember. Why? Why do we need the increasing order of the energies of these subshells? Because as per our Bose principle is concerned, electrons are to be filled in the subshells on the basis of their increasing energies. I'm sure it's clear to everyone, right? Yes? Okay. So let's exactly get to know how this electronic configuration is written. But before that, there are a few more rules which you need to know, okay? Yeah? So I hope you got to know the increasing order of energies of the subshells in case of multi-electron system. Remember, in case of hydrogen, if I particularly talk about hydrogen, for hydrogen, n plus L rule is not valid. N plus N rule is not valid. In case of hydrogen, what is going to be the increasing order of energies of different subshells? Remember, in case of hydrogen, I'm talking about the hydrogen atom in particular, right? I'm talking about hydrogen atom in particular, okay? So in case of hydrogen atom, 1s has got the least energy, followed by 2s. 2s and 2p, they have got same energy, followed by 3s. 3s, 3p and 3d, they have got same energy, right? Similarly, 4s, 4p, 4d and 4f, they have got same energy in case of what? In case of hydrogen atom in particular, right? Which has got only one electron in it, okay? Yes? So remember, in case of hydrogen atom, in case of the single electron species hydrogen atom, okay? The subshells which belong to the particular shell, they'll be having same energies. For example, 2s and 2p, these are the subshells of the second shell, right? So they have got same energy. 3s, 3p and 3d, they are the subshells of a particular shell. They have got the same energy. 4s, 4p, 4d, 4f, right? They are the subshells of the particular shell having the same energy. I'm sure it's clear to everyone, okay? Yeah? Now we will, at the same time, remember one more thing. I hope this is clear to everyone, right? Okay? And this concept, this is basically the increasing order of the energies for the hydrogen atom, for the single electron species hydrogen atom, whereas in case of all the multi-electron systems, in case of all the multi-electron species, this order is not to be followed. The other one, which I showed you earlier, that is N plus L rule, that is to be followed, right? I'm sure this is clear till here, right? Okay. Now people, this was about our Bose principle. Let's move on. Let's talk about a few more important things, okay? According to this principle, filling of electrons in different orbitals is done in increasing order of their energies. That is, lowest energy orbital will be filled first. Point number one. This is something which we have discussed, right? Then we saw the Bohr-Bury's rule. The orbitals having less n plus L value will have less energy. This is something which we discussed, right? In orbitals having same n plus L, that orbital which has got the lesser value of n will have lesser energy. This is something which we discussed too, right? And this is going to be the energy order in case of the multi-electron species, which we discussed too, right? And similarly for single electron species like hydrogen, n plus L rule is not valid. Energy of orbital depends only upon the value of n, as you saw, right? It does not depend on the value of L. For the single electron species like hydrogen, the energy of the orbital only depends on the principal quantum number. It does not depend on the azimuthal quantum number, right? Because we saw, few minutes back, I have shown you the order. For every particular shell, there are some subshells, and those subshells, in case of hydrogen, in case of single electron species, have got the same energies, right? I'm sure it's clear till here. Okay, this is valid for what? This is valid for single electron species. Perfect. And this is the energy order for the single electron species, which I showed you a few minutes back, right? First 1s, then 2s and 2p will have same energy, right? Then 3s, 3p, 3d will have same energy, and so on, right? And at the same time, you can see just one thing. In case of single electron species, the energy of the subshells, it only depends on the principal quantum number. It is independent of the azimuthal quantum number. Yeah? Okay. I hope this is clear to everyone. Now there is something called as degenerate orbitals. Right? How do we define these degenerate orbitals? Orbitals having same energy is something which we call as degenerate orbitals, right? Okay. I'll be giving you its more appropriate definition in some time. Just understand one thing, people. If I talk about p subshell in particular, in case of p subshell, how many orbitals do we have? We have got 3 orbitals. One is called as px, one is called as py, one is called as pz. Can I say these are the orbitals which belong to the same subshell, right? The orbitals belonging to the same subshell having same energy is something which we call as degenerate orbital. So your px, py, pz, their energy is same. They belong to the same subshell as well. I'll be calling this px, py and pz as degenerate orbitals, right? Okay. Similarly, people, if I talk about d subshell, in case of d subshell, how many orbitals do we have? We have got some 5d orbitals, right? We have got some 5d orbitals, 1, 2, 3, 4 and 5, right? One is called as dxy, one is called as dyz, one is called as dzx, one is called as dx square minus y square, one is called as dz square. These are the 5 orbitals of your d subshell. These 5d orbitals, they'll be having same energies, right? And they are belonging to the particular subshell. So I'll be again calling them as the degenerate orbitals. So basically, what are degenerate orbitals? Degenerate orbitals are the orbitals of the same subshell which have got same energy in absence of electric or magnetic field. Right? In absence of electric and magnetic field, these will be definitely having same energies, right? Similarly, in absence of electric and magnetic field, these will be having same energies and they are belonging to the same subshell, so I'll be calling them as the degenerate orbitals. I'm sure this is clear to everyone, yeah? Right, people? Now let's move on. Let's talk about few more interesting things. Okay, see this p subshell containing px, py and pz. In absence of electric field, these 3 orbitals will have same energies and belonging to the same subshell. I'll be calling this px, py and pz as the degenerate orbitals. I'm sure this is clear to everyone. Similarly, in case of d subshell, right, there are 5 degenerate d orbitals. Okay, this is degenerate, this is not regenerate. Okay, so how do we define the degenerate orbitals in particular? Degenerate orbitals, these are the orbitals of a particular subshell, right? Or I can say orbitals of a particular subshell are degenerated in absence of the external field, right? In presence of the external magnetic field or electric field, they split into different energies, hence degeneracy is lost. See what it means exactly. If I talk about p subshell, in case of p subshell, how many p orbitals do we have? We have got 3 p orbitals, one is px, one is py, one is pz. In absence of electric field and magnetic field, their energy is equal, right? But in presence of electric or magnetic field, their energy becomes different. For example, let's assume in presence of external electric or magnetic field, this is the energy diagram. For example, right, their energy becomes different in case of what? Their energy becomes different in case of external electric or magnetic field, or I can clearly say their degeneracy is lost. Right? Why is that? Because of the presence of external electric or magnetic field, right? Whereas without the presence of external electric and magnetic field, right, they will be absolutely always degenerate if they are belonging to the same subshell. Okay, I'm sure everything is clear till here. Now comes one more rule which you must remember, then only we'll be able to write the electronic configurations, right? Now what is this rule all about? This is what we call as Pauli's exclusion principle. Now there is one simple statement from this Pauli's exclusion principle, people. According to this principle, no two electrons in an atom can have same set of 4 quantum numbers. No two electrons in an atom can have same set of 4 quantum numbers. What does that mean? For example, if I'll be having some p6 configuration, if I talk about p6 configuration, see, this simply means in the p subshell we have got some 6 electrons. In p subshell we have got some 6 electrons. Let's say this is something which I'm writing, 3p6 for example, 3p6. In case of p subshell, how many orbitals do we have? We have got 3 orbitals, right? How many electrons are there? 1, 2, 3, 4, 5, 6, right? And this subshell, this p subshell, it belongs to shell number 3. It belongs to shell number 3, right? Okay. This p subshell belongs to shell number 3. Let's call this as px. Let's call this as py. Let's call this as pz, right? Let's assume the value of m for pz is 0. The value of magnetic quantum number for py is -1. Let's assume the value of magnetic quantum number for px is, for example, +1. Okay, let's assume this. Okay. Now, people, from this configuration, if I'll be selecting, let's assume 2 electrons, right? Let's assume I'm selecting this electron, I'm selecting this electron, and at the same time, for example, I'm selecting this electron, right? Now, as per Pauli's exclusion principle, no 2 electrons in an atom will have same set of 4 quantum numbers, right? What does that mean? Understand. See, guys, this electron, it belongs to, first of all, shell number 3. So for this electron, the value of n is 3, right? This electron belongs to p subshell. For p subshell, the value of L is 1, right? It belongs to px. For px, the value of m is +1. And its arrow upwards, that means it's moving clockwise, so its spin is +1/2, right? So these are the values of 4 quantum numbers for this electron. Similarly, if I want you guys to let me know the 4 quantum numbers of this electron, you can tell me that too, yeah? If I talk about this electron is again present in shell number 3, so n value is 3, right? Okay. This electron is present in p subshell, so the value of L is 1, because for the p subshell, the value of L is 1, right? This electron is present in pz orbital, and for pz orbital, the value of m is 0, right? Okay. Now, similarly, it is arrow downward, that means it's moving with anti-clockwise spin, so spin is -1/2, right? So if you look at these 2 electrons, are these 2 electrons having same set of 4 quantum numbers? These are not having same set of 4 quantum numbers, as simple as that. Similarly, if you select any of the 2 electrons in the atom, definitely one of the quantum number will be different, right? One of the quantum number will be different for the 2 electrons, which you would have selected, right? Okay, I'm sure every single thing is clear till here, right? Perfect? Absolutely, guys, right? So what is Pauli's exclusion principle all about? According to Pauli's exclusion principle is concerned, no 2 electrons in an atom can have same set of 4 quantum numbers. I'm sure it's clear to everyone, right? And there is one more way. An orbital can accommodate maximum of 2 electrons with opposite spin. This is one more statement of it, so you need to remember this as well. See, if I talk about S subshell, right? This is S subshell. Over here I'm writing something as P subshell, right? Over here I'm writing as D subshell, something like that, right? In case of S subshell, there is only 1 orbital. In case of P subshell, there are 3 orbitals, right? In case of D subshell, there are 5 orbitals. 1, 2, 3, 4, 5. 5 orbitals. Now, every orbital, as per this principle is concerned, every orbital accommodates maximum of 2 electrons. If I talk about this orbital, it will accommodate maximum of 2 electrons. If I talk about this particular orbital, it will accommodate maximum of 2 electrons. This will accommodate maximum of 2 electrons. This will accommodate maximum of 2 electrons. And eventually, your P subshell, it accommodates maximum of total 6 electrons, right? Similarly, every orbital over here will accommodate maximum of 2 electrons. Those 2 electrons will be definitely having opposite spin, right? One arrow upwards, one arrow downwards, right? One moving clockwise spin, one moving with anti-clockwise spin, right? Similarly, we have got some 5d orbitals over here. 5d orbitals means every orbital accommodates maximum of 2 electrons. So how many total electrons are accommodated over here? Total 10 electrons are accommodated in case of D subshell, right? And so once more I'm telling you the same thing, an orbital can accommodate maximum of 2 electrons, and both the electrons will be having the opposite spin, right? I'm sure it's again clear to everyone, right? Yes? Okay? Now we will understand few more things. Okay, this is something which we have discussed in the last session as well. If you want to calculate number of orbitals in a particular shell, if you want to see how many orbitals are there in shell number 1, how many orbitals are there in shell number 2, how many orbitals are there in shell number 3, it is simply given by the formula n square, right? This is the formula by means of which you can calculate the maximum number of orbitals in a particular shell, right? Similarly, maximum number of electrons which can be accommodated in a particular shell is given with the formula 2n square, right? This is something which you all must be knowing again, right, people? Okay. Now, after this, what we are going to do over here? Let's exactly see what we are going to do. See, guys, let's move on. I'm sure these two formulas are clear to everyone, okay? This is the question on your screen. Have a look on this question carefully. How many maximum electrons can be accommodated in 3d orbital? I want you guys to let me know the answer of this question in the chat box. I'm looking at your chats. I want you guys to give it a try and let me know its answer. Let me know fast. How many maximum electrons can be accommodated in 3d orbital? Can you just let me know its answer in the chats? I'm looking at your chats only. Just let me know fast. It's simple, guys. It's simple. How many maximum electrons can be accommodated in 3d orbital? He's mentioning 3d orbital. He is not mentioning 3d subshell. If he would have mentioned 3d subshell, then your answer would have been 10. Why? Because in case of d subshell, there are 5 orbitals and every orbital accommodates maximum of 2 electrons. So total 10 electrons will be accommodated in 3d subshell. But he's asking about 3d orbital. He's asking about one of the orbital of the 3d. And every orbital accommodates maximum of 2 electrons. So every orbital accommodates maximum of 2 electrons. So what is going to be the answer of this question? It's going to be 2. If the question was how many maximum electrons can be accommodated in 3d subshell, the answer would have been 10. But the question says how many maximum electrons can be accommodated in 3d orbital, the answer is going to be 2, because every orbital, be it s, be it p orbitals, be it d orbitals, every orbitals will accommodate a maximum of 2 electrons, that too with opposite spin, right? I'm sure again this is clear to everyone. Okay, right, let's move on to something called as Hund's rule of maximum multiplicity, right? This is the final rule. After going through this rule, I'll be exactly showing you how do we write the electronic configuration of different elements, right? I'm sure every single thing is clear till there, right, people? Let me know in the chats first. Yes, Aishwarya, I remember. Okay, so people, what this Hund's rule of maximum multiplicity is all about. This is the statement which you need to remember. Then I'll show you the application part of this statement as well. According to this principle, out of different arrangements of same electronic configurations, the arrangement which has got the higher multiplicity will be more stable. What is meant by this statement? What is meant by this statement? How can we understand this statement? First of all, I want you guys to go through this statement again. According to this principle, out of different arrangements of same electronic configuration, the arrangement which has got higher multiplicity will be more stable. Higher multiplicity will be more stable. That arrangement whose multiplicity will be higher will be more stable. Now the point is, how do we calculate multiplicity? There is a formula for that. There is a formula for that to calculate multiplicity. That configuration which will be having more multiplicity will be definitely more stable. What does that mean exactly? Just have a look, people, exactly what I'm talking about. This is the formula by means of which we can calculate the multiplicity, right? I'm talking about the same configuration, right? For the same configuration. Let's say P3 configuration we have taken, right? This is the P3 configuration we have taken, right? P subshell is containing 3 electrons. P subshell is containing 3 electrons. Let's assume it's one of the configurations like this. Let's assume this is one of the configuration of P3. 2 electrons here, 1 electron here, okay? Let's say one more configuration is like this. 1 electron here, 1 electron here, 1 electron here, right? These are the two possible configurations of P3 which I'm giving to you, okay? One of them is absolutely going to be wrong, right? But that is not the debate right now. I need to see which configuration of P3 is more stable. That configuration of P3 will be more stable, which will be having more multiplicity. Now the point is, how do we calculate multiplicity? In order to calculate multiplicity, this is the formula. Multiplicity is equal to S plus 1. S is basically sum of spin. S is basically sum of spin. What does that mean? Understand. See guys, if I need to calculate the multiplicity for this configuration, okay, say this electron is going clockwise spin, so plus 1 by 2, this is minus 1 by 2, cancel out. This will be plus 1 by 2, so the sum of the spin is simply going to be plus 1 by 2, right? This is the total spin. S is equal to plus 1 by 2. If S is plus 1 by 2, put the value of S in this equation. So instead of S, you'll be writing 1 by 2. 2 got cancelled. 1 plus 1 came out to be 2. So multiplicity of this P3 configuration right here is going to be 2, right? Similarly, this is one more P3 configuration. Let's calculate multiplicity for this configuration as well, okay? One electron here, one electron here, one electron here. So plus 1 by 2, plus 1 by 2, plus 1 by 2 comes out to be 3 by 2, plus 3 by 2 when we add them, right? Okay. Yes, people? So total spin of this type of P3 configuration is simply going to be plus 3 divided by 2, yeah? If the total spin of this configuration is plus 3 divided by 2, put the value of S over here as 3 by 2. If I put the value of S as 3 by 2, it is going to be 3 by 2, 2 got cancelled, 3 plus 1 comes out to be 4. So multiplicity of this P3 configuration is more, right? Multiplicity of this P3 configuration is 2, multiplicity of this P3 configuration is 4, right? Or, right? So for the same configuration, right, for the same configuration, that arrangement which shows maximum multiplicity will be more stable, right? So which one is more stable configuration among the two? Is the first one more stable or second one? Second one is absolutely more stable than the two, right? Now we can conclude something from here, right? This is, for example, your Px, this is Py, this is Pz. All these orbitals, they are belonging, for example, to the same subshell, right? I can say something like this. I got to know this configuration is more stable. So this is going to be the actual configuration of P3. This is going to be the actual arrangement of electrons in P3 configuration, right? I can conclude one thing. I can say pairing of electrons won't be done. Pairing of electrons won't be done in these degenerate orbitals unless each degenerate orbital gets one electron with the same spin, right? Yes? Okay? Right, people? From this configuration, I can conclude one thing. Pairing of electrons won't be done in the degenerate orbitals unless each degenerate orbital gets one electron. That too with the same spin, right? That is absolutely one more conclusion of this Hund's rule of maximum multiplicity, right? First of all, let's take one more example, then we'll exactly see what it's all about. Let's say I'm talking about P4 configuration. Let's say I've got P4 configuration, right? Let me draw two arrangements for this P4 configuration. Let me draw two arrangements. 1, 2, 3, 4. This is, for example, one of the arrangement of P4. I'm going to make one more arrangement of this P4 configuration, right? 1, 2, 3 and 4. These are the two arrangements for this P4 configuration, right? Now I need to see which one is more stable. The one which will be having more multiplicity will be definitely more stable, right? Now how do we calculate multiplicity? This is the formula to calculate multiplicity, right? So let's calculate the total spin for this arrangement. Plus 1 by 2 minus 1 by 2 cancelled out. Plus 1 by 2 minus 1 by 2 cancelled out. So spin of this is 0. If the spin of this arrangement is 0, if the total spin of this arrangement is 0, so what is the value of multiplicity for this arrangement? It's going to be, this term is 0, this is 1. So m value is coming out to be 1, right? For this one, what is the m value coming? This and this gets cancelled out. So plus 1 by 2, plus 1 by 2. Plus 1 by 2, plus 1 by 2. The value comes out to be 1. This is the value of total spin. If the value of total spin came out to be 1, so it's going to be 2 plus 1, 3. So multiplicity is going to be 3, right? So in case of P4 configuration, which arrangement has got more multiplicity? Second one, right? That arrangement of the same configuration having more multiplicity will be more stable as per Hund's rule, right? So this is absolutely going to be the correct arrangement of electrons in for your P4 configuration, right? I'm sure every single thing is clear to everyone, right? You can let me know in the chats if every single thing is clear, right? Now, after redox reactions, we'll be starting the periodic properties on neat late, right? I'm sure every single thing is clear. So let me directly move on to certain things. Note, pairing won't occur in the degenerate orbitals unless each degenerate orbital gets one electron each, that too with same spin. Yeah, I'm sure every single thing is clear. Okay. Now people, let me exactly show you how do we write the electronic configuration. After writing the electronic configuration, I'll show you some exceptional electronic configuration and their reasons as well. Okay, let's get going. Let's exactly see how do we write the electronic configuration. Okay, so how many rules are to be followed in order to write the electronic configuration? Abba's principle, right? Abba's principle, Pauli's exclusion principle, right? Okay, and Hund's rule. These are certain rules which you need to follow while writing the electronic configuration of different elements. Yeah. Okay, let's exactly see, guys, how do we write the electronic configuration. As per Abba's principle is concerned, electrons are to be filled in the orbitals on the basis of their increasing energy. So 1s comes first, then comes your 2s, then comes your 2p, similarly comes your 3s, similarly comes your 3p, similarly comes 4s, then comes 3d, and so on, right? And so on, okay, and so on, okay. Now guys, understand. Your s subshell contains only one orbital, s subshell contains only one orbital, p subshell, it contains 3 orbitals, s subshell contains 1 orbital, p subshell contains 3 orbitals, right? S subshell contains 1 orbital, d subshell absolutely contains 5 orbitals, 1, 2, 3, 4 and 5, yeah, 5 orbitals, okay. If I start with hydrogen, in case of hydrogen, how many electrons are there? There is only 1 electron present. Now fill the electron in this one. So I got the configuration of hydrogen as 1s1, as simple as that. If I talk about helium, in case of helium, there are 2 electrons present in total, right? So put 1 more electron over here, but with the opposite spin, right? In an orbital contains 2 electrons. An orbital can accommodate maximum of 2 electrons, that too with opposite spin, right? So helium configuration is going to be simply 1s2, right? Hydrogen, helium. If I talk about lithium, lithium has got some 3 electrons, right? 2 electrons are already present, put 1 more electron over here. So its configuration becomes what? Its configuration becomes 1s2, 2s1. Yeah. Similarly, hydrogen, helium, lithium. Then if I talk about beryllium, in case of beryllium, there are 4 electrons, right? 3 are already filled. Now put 1 more electron over here with opposite spin, right? So it's going to be 1s2, 2s2. Yeah. Similarly, if I talk about boron, 5 electrons in total. 4 are already filled, put 1 electron over here. So the configuration becomes 1s2, 2s2, 2p1, correct? If I talk about carbon, carbon has got some 6 electrons. 5 are already filled. Now it is the turn for 6 to get filled. Should I do the pairing? No, I won't be doing the pairing. I'll fill these degenerate orbitals with 1 electron each with the same spin, right? Then only I'll be doing the pairing, right? Okay. Naveen, tomorrow I'm starting the redox. Tomorrow I'm starting the redox. Yeah? Okay. So in case of carbon, what is going to be the electronic configuration? Is going to be 1s2, 2s2, 2p2. Correct? Similarly, if you talk about nitrogen, nitrogen has got some 7 electrons. Now out of 7, 6 are already filled. So put 1 more electron over here. What is the configuration of nitrogen then? It's going to be 1s2, 2s2, 2p3. Right? Okay. Now similarly guys, you can write the electronic configuration of anything. For example, I need to write the electronic configuration of chlorine. Chlorine has got some 17 electrons. Chlorine has got some 17 electrons. So it's going to be 1s2, 2s2, right? 1 electron over here, 1 electron over here, 1 electron over. So it's going to be 2p6, 3s2, 3p5, 3p5, right? So this is the electronic configuration of chlorine, 17 electrons. See, I have accommodated the 17 electrons in these orbitals, 2 over here, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 5, 17, right? So its configuration becomes 1s2, then you write 2s2, then you write 2p6, then you write 3s2, and then you write what? You write 3p5. This is the electronic configuration of chlorine, as simple as that, right? I'm sure it's clear to everyone, right people? Now there are certain exceptions as well. If you talk about chromium, chromium has got the atomic number of 24, right? It has got the atomic number of 24. Its expected configuration, its outermost expected configuration should be what it should be? Its outermost expected configuration should be 3d4, 4s2. This should be the expected outermost configuration of chromium. This is the expected outermost configuration of chromium. But this is not the actual one. This is not the actual one. There are certain exceptions. So what is the reason for those exceptions? You'll get the idea in some time, right? Okay. But right now, this is the expected electronic configuration of chromium. So 3d4. 3d4 means 1, 2, 3, 4, and this is 4s2. Correct? This is the expected configuration of chromium. But what is the actual configuration of chromium? If I talk about the actual configuration of chromium, one of the electron from 4s enters into 3d, then it becomes 3d5, 4s1. Then it becomes 1, 2, 3, 4, 5, 3d5 and 4s1. This is the actual configuration. This is the expected configuration. What is the reason for this behavior? Why there is exceptional behavior in case of chromium, right? You'll get the idea in some time, right? Okay. Similarly, if I talk about copper, copper has got the atomic number of 29. So its expected configuration is supposed to be 3d9, 4s2. This is the expected configuration, right? But what is the actual configuration of copper? What is the actual configuration of copper? This is the expected one, but its actual one is like this. See guys, this is the expected one, 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And 4s2. This is the expected one, but what is the actual one? Let me draw the actual one. One of the electron from here will enter here, right? So its configuration becomes something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1 electron over here, right? So expected configuration was 3d9 4s2, but its actual configuration is 3d10 4s1. What is the reason for chromium and copper to show the exceptional configuration? What is the reason for that? The reason is more stability. The reason is more stability of half-filled configuration, more stability of the exactly half-filled configuration, right? And in case of chromium, and in case of copper, it is going to be completely filled configuration, which you are getting when one of the electron goes into your 3D, right? What is the reason for these configurations? What is the reason for this type of configuration and this type of configuration to be stable? Okay, that's something which I'll be telling you now, right? That's something which I'll be telling you now. So, since in case of chromium, this is the expected one, this is the actual one. Actual one is more stable due to half-filled configuration, and in case of, just a second people, in case of copper, 3d10 4s1 is more stable than 3d9 4s2 because of completely filled your d subshell, right? Now there are two more things which you need to remember. The stability of fully filled configuration is the maximum, followed by half filled, followed by partially filled, right? This is something which I'll be explaining in some time, okay? Now, the energy difference, remember, the energy difference between 3d and 4s is very small. Therefore, they almost become degenerate. Hence, shifting of electrons easily takes place from 4s to 3d to get the extra stability, right? See, I told you in case of chromium, one of the electron from 4s enters into 3d so as to get what? So as to get half-filled configuration, right? Because half-filled configuration is more stable, right? 3d5 configuration is more stable than the 3d4, yeah? So since in case of 3d and 4s there is slight energy difference between the two orbitals, in case of 4s and 3d, there is slight energy gap between the two subshells, right? Between these orbitals there is slight energy gap. So you can almost consider them as they degenerate. That's why shifting of electron from 4s to 3d is happening due to the attainment of your extra stability in case of your 3d5 configuration, right? Okay. Now we will have a look. Just a second. Now we will have a look. In case of copper, this is something which I told you, right? 3d10 4s1 is the actual configuration because due to the more stability, due to the fully filled configuration, right? Okay, now the point is, how come your half-filled configuration is more stable? There are two reasons for the half-filled and fully filled configuration to be more stable, right? The first reason is symmetrical distribution of electrons. People, it is the old age statement, symmetry leads to stability, right? Symmetry leads to stability. If I talk about D5 configuration, if I talk about D4 configuration, if I compare D4 configuration with D5 configuration, see guys, if I write D4 configuration over here, this is 1, 2, 3, 4, 5, right? 1, 2, 3, and 4. Similarly, if I write D5 configuration, this is your D5 configuration all about 1, 2, 3, 4, 5. So 1 electron in each orbital, right? I'm telling you this configuration is more stable, right? Because symmetry leads to stability. This one is more symmetrical distribution of electrons. In this configuration, there is more symmetrical distribution of electrons. And wherever there will be more symmetrical distribution of electrons, that configuration is absolutely going to be more stable. That's why your D5 configuration is generally more stable than that of D5 than that of your D4 configuration, right? Or you can simply conclude one thing: this half-filled configuration is going to be more stable than that of partially filled configuration. This is not completely half-filled. This is not exactly half-filled. It's partially filled. This is the reason why, due to the symmetrical distribution of electrons, by means of which it attains more stability, right? That's why your D5 configuration is considered to be more stable than that of D4 configuration. That's why your half-filled configuration is more stable than that of partially filled configuration, right? This is one of the reasons. Symmetrical distribution of electrons. The second reason is something which we call as exchange energy. The second reason is something which we call as exchange energy. This is the second reason by means of which we can conclude why your completely filled or half filled configurations are more stable, right? See guys, these are the degenerate orbitals containing electrons. Yeah, these are the degenerate orbitals containing electrons. So if these are degenerate, they almost have got similar energies, right? They have got same energies first of all. Now this electron over here, it can exchange its position with this electron. Both are having same spin. At the same time, this electron will shift here. This could have exchanged its position with this one. At the same time, this would have come here. At the same time, this electron would have exchanged its position with this one. At the same time, this electron would have come here. So how many exchanges are possible for this electron? 1, 2, and 3. There are 3 exchanges possible for this electron, right? Similarly, if I'll ask you how many exchanges are possible for the second electron, see, second electron can go to this position, but it's already counted. Now this second electron, it can go here or it can go here, right? Yes. So there are 2 exchanges possible for this one. There are 2 exchanges possible for this one, right? Similarly, there will be 1 exchange possible for this one. So how many total exchanges are possible in case of D4 configuration? 3, 2, 5 plus 1, 6. So there are 6 exchanges possible in case of D6 configuration, sorry, D4 configuration. Similarly, if I talk about D5 configuration, how many exchanges are possible here? See, this electron can shift its position here. With this one, it can exchange its position, right? So there are 5 exchanges possible for this one. Similarly, there will be 4 exchanges possible for this one, 3 for this one, 2 for this one, 1 for this one, right? Right, people? In case of D5 configuration, wait, I did something mistake. 1, 2, 3, and 4. There are 4 exchanges possible for this electron, 3 for this one, 2 for this one, 1 for this one, and 0 for this one. So how many total exchanges are possible in case of D5 configuration? 4 plus 3, 7 plus 2, 9 plus 1, 10. So there are basically 10 exchanges possible in case of D5 configuration. Remember, wherever exchanges are more, more is the energy released. More is the energy released. The amount of energy released when the electrons are exchanged in the same subshell. When the electrons exchange their position in the same subshell, right? That amount of energy released is something which we call as exchange energy. And more the exchange energy, that means more the energy released during the exchange of electrons, right? More is going to be the stability, right? So number of exchanges over here are more. If number of exchanges over here are more, so more will be the energy released. More the energy released means more the stability. That's why your D5 configuration is more stable than that of your D4 configuration. I'm sure it's again clear to everyone. People, you can let me know in the chats if every single thing is clear till here. Right? Okay? Right? So more the exchange, more the energy release, more the stability, right? If I want you guys to compare the stability of these configurations, this is P1 configuration, this is P2, this is P3. P3 will be more stable. Why? Because in case of P3, there are more exchange. More exchange means more energy released. More energy released means more stability, right? As simple as that. Yeah? Now there is one term called as magnetic moment. Magnetic moment is something which we represent by nu. And its formula is going to be under root of n into n plus 2 Bohr magnetrons. Bm stands for Bohr magnetrons. And n stands for the number of unpaired electrons. N stands for the number of unpaired electrons. N stands for the number of unpaired electrons. Right, people? Now understand. Nivedita, you can write it. Atomic number. You can write it on your own, right? Based on the same rule. Okay. Okay, what is this mu? Mu is something which is magnetic moment. Let me exactly show you how do we calculate magnetic moment. But before talking about magnetic moment, remember that species whose magnetic moment is non-zero, we call that species as paramagnetic species. Paramagnetic, right? And that species whose mu value is equal to 0, we call that species as the diamagnetic species. Diamagnetic species, right? One is paramagnetic, one is diamagnetic. If for any species, magnetic moment value comes out being non-zero, that species is going to be paramagnetic. If for any species, mu is 0, that's something which is going to be diamagnetic, right? For example, let me take certain cases. Let's say I'm talking about Mn plus 2. Mn plus 2. I need to see is it paramagnetic or diamagnetic, right? If I write the outermost configuration of manganese,
If I write the outermost configuration of manganese, it is 3d5 4s2. But this is Mn di positive, that means you are taking 2 electrons out from here. So take the 2 electrons out, so it becomes 4s0, 3d5. In case of 3d5 configuration, how many unpaired electrons do we have? We have got some 5 unpaired electrons, so n value is 5. If the value of n is 5, you can calculate mu over here, which is going to be under root of n into n plus 2. So 5 plus 2, 7. 7 multiplied by 5, 35. So root of 35 Bohr magnetrons is the value of magnetic moment for Mn di positive, right? So is the value of mu coming out to be 0 or non-zero? It's non-zero. That means this species is absolutely going to be paramagnetic. As simple as that, right? Similarly, you can take any case, you can calculate the magnetic moment in Bohr magnetrons. You simply need to know how many unpaired electrons are there, right? Remember, more the unpaired electrons present, more is going to be the paramagnetism. Right? Let's do one of the question based on the same thing, yeah? This is the first question. Let's try to do this. Which of the following has got the maximum number of unpaired electrons? Mg di positive. Magnesium, its atomic number is 12, right? So 1s2, 2s2, 2p6, 3s2, correct? But this is Mg di positive, so you are taking 2 electrons out. Right? Is there any unpaired electron? There is no unpaired electron. This p, it has got only 3 orbitals, and all the 3 orbitals are occupied, so unpaired electrons are 0. If unpaired electron is 0, that means this one is going to be diamagnetic, right? Titanium tripositive, scandium, titanium, right? The outermost configuration I'm writing as 3d2, 4s2. This is the outermost configuration of titanium, right? 3d2, 4s2. Now take 3 electrons out from here because it's tripositive. So 2 electrons have to be taken out from here, 1 electron have to be taken out from here, so there will be only 1 electron. So there is only 1 electron in 3d, so the number of unpaired electrons over here is 1. If the number of unpaired electrons is 1, is it going to be paramagnetic or diamagnetic? Calculate mu. Mu is simply going to be equal to under root of n into n plus 2. So the value comes out to be 1.73 Bohr magnetrons. So mu value coming out to be non-zero means it is paramagnetic. What I was supposed to calculate? Which of the following is maximum number of unpaired electrons? Okay. So this one is paramagnetic. It has got 1 unpaired electron. V tripositive. Scandium, titanium, vanadium. Vanadium means 3d3, 4s2. Take 3 electrons out because it's tripositive. So after taking 3 electrons out, it becomes only 3d2 configuration. So how many unpaired electrons are there? There are only 2 unpaired electrons, right? In case of Fe dipositive, iron has got the configuration of 3d6, 4s2, but this Fe dipositive, take 2 electrons out, it becomes 4s0, so there are 4 unpaired electrons in case of 3d. So which of the following has got the maximum unpaired electrons? Fe dipositive. If I'll ask you which of the following has got the maximum paramagnetism, you will say Fe dipositive because it has got more unpaired electrons. If I'll ask you which of the following has got the maximum magnetic moment, you will absolutely say Fe dipositive only, right? I'm sure it's clear to everyone. Perfect. Okay, calculate the magnetic moment of the following species. You can do it on your own now, I believe. Fe di-positive configuration. Take 2 electrons out, its configuration finally becomes 3d6. So there are 4 unpaired electrons. If there are 4 unpaired electrons, under root of n into n plus 2, 4 plus 2 is 6, 6 4 is 24. So root of 24 Bohr magnetrons is the value of mu's magnetic moment. Cobalt di-positive, iron cobalt, 3d7 4s2. Take 2 electrons out, so 3d7 is the configuration, right? 3d7 configuration means n value is 3. N value is 3, number of unpaired electrons are 3. If unpaired electrons are 3, you can calculate as a magnetic moment as under root of n into n plus 2 Bohr magnetrons. Solve it, get it done. I'm sure it's clear to everyone, right? So in the similar way, you can calculate the magnetic moment of the other species as well. Okay, the correct ground state configuration of chromium. Chromium, its correct ground state. Is it going to be 3d4 4s2? No, it's going to be 3d5 4s1, right? It's going to be 3d5 4s1, correct? Yeah, it's going to be 3d5 4s1, which is going to be option D. Right, people? The orbital diagram in which the Abbas principle is violated. In which of the orbital diagram Abbas principle is violated? As per Abbas principle, electrons are to be filled in the orbitals on the basis of their increasing energies. So that orbital which has got the lowest energy will be getting electrons first, okay, will be getting paired first. For example, see guys, if you look at option B, is this orbital completely filled? This orbital is not completely filled, right? So first, this orbital should have been completely filled, then only the filling of electrons should have been done in this subshell, right? But in this one, your S subshell is not completely filled, still then your P subshells are filled, right? So over here, your Abbas principle is getting violated. So in case of option B, Abbas principle is actually getting violated, right? Okay, I'm sure it's clear to everyone. Okay, any p orbital can accommodate up to what? Any p orbital can accommodate up to what? Can you let me know its answer as well? Any p orbital can accommodate up to what? 4 electrons, 6 electrons, 2 electrons with same spin, 2 electrons with opposite spin. What is going to be the answer of this one? What is going to be the answer of this one? See, any p orbital, he's not saying p subshell, he's saying p orbital. Every orbital accommodates maximum of 2 electrons, that too with opposite spin, right? 2 electrons with opposite spin. I'm sure it's again clear to everyone. Okay. One more question, people. 4d, 5p, 5f, 6p orbitals are arranged in the order of their decreasing energies. Okay. So how do we arrange them on the basis of their decreasing energies? What do I need to do? I need to calculate n plus L value. What is the n plus L value for 4d? N value is 4. For d, L is 2. So 4 plus 2 comes out to be 6. So n plus L is 6. 5p, 5 plus 1, 6, right? 5f, 5 plus 3 is 8. Okay. 6p, 6 plus 1 comes out to be 7. So which orbital, which subshell has got the lowest n plus L value? These two have got lowest n plus L value. Same 6, right? But this is having lowest n value. So 4d is going to have the lowest energy, right? 4d is going to have lowest energy, right? Now people understand. Among 6p and 5f, among 6p and 5f, 5f has got more energy than that of 6p, so option A is the answer of this question, right? Naveen, tomorrow we are going to start the redox reaction on NEET lead channel, right? Tomorrow I'm saying. So people, with this, your electronic configuration part is done and dusted, okay? Right? I'm sure every single thing is clear to everyone. So this is just one thing left which I would like to share with you. If you have not got enrolled into the actual Vedantu classroom, right? Okay, which happens on the actual Wave platform, right? Vedantu's actual platform, apart from the YouTube classes, it's high time for you guys to get enrolled in any of these plans, right? In order to get trained by us in all the 3 subjects, physics, chemistry, mathematics, right? You can take any of these plans, yeah? Okay, and this is the course fees for 2 years. It's a 2-year classroom program. This one is 2-year classroom program. This one is 2-year classroom program. Now it's going to be entirely your wish to select the plan for yourself and get trained by us on the actual Vedantu platform, right? And people, if you are new to Vedantu and you have no idea how these Vedantu classrooms look like, what it's all about, am I getting benefit or not? You can take any one of these plans for a month. Vedantu has kept an option for that as well, right? You can take any of these plans for a month. For 1 month, you need to pay some 2,700 for this one, right? And how do we get enrolled? Click on any of these plans, right? Use the coupon code WBPRO, get some additional 10% off, right? Definitely you'll be getting benefit from this, okay? Now people, exactly let me show you how to get enrolled in this one, okay? See, this is the video which you guys are currently watching. So let me drag the video a little down. I need to click on this show more. After clicking on this show more, so there are a lot of links which you are getting. Right here. Okay. Subscribe to Vedantu Pro. After clicking on this, where do I redirect? See, over here you need to choose your plan. If you are going to for light, click on this. Going for classic, click on this. Going for plus, click on this. For example, I'm going for light. Okay. You can try this course for a month, or you can buy the complete course by using the coupon code of WSPRO, right? You need to click on this. After clicking on this, what do you need to do? You simply need to give your number, email on which you get the OTP and get enrolled and get trained by us on the actual Vedantu platform, right? And people, at the end, if you have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe the channel as well, okay? So this was all from my side in tonight's session. I'll see you guys tomorrow at the same time. Till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye.